are in Group B of Computer Engineering for Linear Algebra. And during the semester, so the class code sorry, this is not the best. So together, we're going to cover CEN 105. Linear algebra, and my name is Arvan. So we'll be together for this semester. I'll cover the theory of the linear algebra class, and together with me in the seminar hours or in the problem sessions, we are going to be with Joanna. Probably some of you have already had a session with Joanna. So it will be two of us. Okay. So we have some students that are joining with a little late, and we have to approve their joining the class. So this is the class of linear algebra. This will be the lecture, and the next, the major piece, the major information regarding the class, you can follow this one from the syllabus. If you go to the website of the department, you can click under the Bachelor Study Programs. In the Bachelor Study Programs, if you select Computer Engineering, in the first semester, you're going to find a link for Linear Algebra. I strongly suggest you go on to the website right away, or it could take me 30 seconds to determine, to find the exact link, and I could do that. And you can go over the syllabus with me at the same time. So you go to the bachelor program, you click to the, okay, I guess I found it. So with this here, I can share with you the link, and we can go together over the syllabus. So in the syllabus, you can find the course objectives, what are the main objectives of this class, and then you can also track down the class material that will be covered for all 14 weeks. And we are going to start, sorry, maybe I can adjust this, I should have done this one a little before. Okay, so, okay, I think this looks fine. This looks good. Okay, anyway. Yeah, so we'll start with the general discussion of matrices and basic operations of matrices, including addition, multiplication, matrix transposes, and similar operations. We're going to talk about the elementary row operations and the row echelon forms. And with elementary row operations, these are very useful, especially when we solve the systems of linear equations. So one of the major topics, it will be systems of linear equations. Now, linear equations, and a linear equation is any expression that looks like this: ax plus by plus cz is equal to d. Okay, so this is a linear equation, and solving systems of linear equations, it means that we have to select, we have to solve a series of these unknowns. And the key word which stands here for linear algebra and linear equation is that all the unknowns, they are to the power 1. Okay? If it was ax squared plus by cubed plus cz to the power 4, this would make this a non-linear equation. But here, all the powers of x, y, and z, which are the unknowns, these are all to the power 1. Those makes this linear algebra or linear equations. Now, whenever you hear the class linear algebra, this algebra, it might include also abstract algebra. We don't cover any of that material. That material is more relevant for mathematics, for students of mathematics department. But here, as engineering students, we are going to cover only the linear algebra part, which deals with the matrices. And more details will be given to you now. So, The first part will be how we are going to cover linear systems of equations. We're going to talk about spatial matrices, like diagonal matrices, triangular ones, how the triangular matrices can be more effectively used in solving systems of linear equations. We're going to talk about the vector spaces and the subspaces. We're going to talk about the concepts of linear dependence and linear independence. And then, after we discuss these major concepts, we come to one of the most important aspects, which is the discussion of the basis. Okay, so a basis, it's a definition of few directions, of few vectors over which we can define the whole space or the whole domain. So the simplest form of defining the basis, giving an example, is, for example, the Cartesian coordinate system. The Cartesian coordinate system is a system which looks something like this. Okay? So we have x and y, so we have the direction along the x and one direction along the y, and we can define any vector as a linear combination of unit vectors along these two directions. These two directions, so we call this one Cartesian coordinate system. And this, the basis or the specific coordinates, we can define them as, let's call this perpendicular. So x and y, they are perpendicular. They are called conjugate. Okay, they are called orthogonal. So these are a couple, not a couple, there are actually more synonyms of these specific keywords. So which means that this key orthogonal and this perpendicular, they are more self-explanatory what they do. And we can also say that the projection of the y vector is 0 onto the x vector. Okay, so this is also one way to call it. And so we are going to talk about the concept of the basis, how to represent a specific data set on a specific basis. Then right away, after the discussion of the basis, we're going to talk about the change of basis. So we can change from one basis to another. Change of basis or between the bases. And what we are going to see often is that we can have a system or an equation defined as ax is equal to b, okay? And then we can have vectors y1, y2, y3, all representing a state or a specific information according to basis 1. So let's consider that this is basis 1. Then we can define, it might happen that the same problem, it can be redefined in a new basis, which is slightly different from the previous one, and we hope for it to be better than the previous one. So we can call this one, this is basis 1, and this is basis 2. Okay, and this problem then it can be defined as, let's call dx is equal to c. Okay, so whatever here we define as ax is equal to b, here we can rewrite or reformulate this problem into dx is equal to c. And now these vectors y1, y2, y3, they can be redefined, and now we write those as capital Y1, capital Y2, and capital Y3. And these are two different bases. What we can do is that we can use a transformation T, which brings us transformation T, a linear transformation, from basis 1 to basis 2. And at the same time, we can move backwards with a linear transformation inverse, going from the second basis to the first basis. This is one of the most impressive aspects of linear algebra, because we can use these transformations in order to solve the same problem in a simpler way, and probably sometimes in a computationally more effective. So we're going to talk about these bases, and the reason that we have a good understanding of bases is that right after that, we're going to talk about eigenvalues and eigenvectors. Here we have eigenvalues, eigenvectors.
Professor?
Yes.
Nuk shikohet fare video, është kualiteti shumë i keq. Po të Gjugjo është në rregull, ama video është keq.
Okay, let's have a look, but I'm surprised because why? Is it blurry or what?
Është si më mirë.
Wait a second. Send resolution. Well, I set this one to the. I thought we were okay actually since we started the discussion. So how is it now? It's blurry.
Oh.
Okay. Is it blurry to the point that you cannot read what I'm writing?
I think now it's better.
Is it?
Yeah.
It's better now.
Now it's okay.
Is it good? Okay, maybe it wasn't. Sometimes the internet connection might diminish the quality. But, okay, can you read what I'm writing? Can you read the board?
Yes, it's okay now.
Yes.
It's good, okay, but your comments are welcome.
I think we can change to settings what video we receive. Like, go to settings, video, receive resolution.
Okay. Thank you for the comments. Probably you can increase the reception, the quality of the received video. Okay.
Yeah.
The settings.
Doesn't help much.
Huh?
But it doesn't help much.
It doesn't. Oh, I'm so. Well, yeah. I'm wondering why is it doing that? Because okay, but if I have a few confirmation that you see it correctly, you can read it.
Now I think it's clear.
You think it's okay? Okay, so let's move on.
Now it's okay.
Okay, that's good. That's better. That's also good. So after the discussion of the basis, which is very essential, very important, we're going to discuss eigenvalues and eigenvectors. Now, eigenvalue and eigenvector, you can look by the terminology. Eigen is a German word, okay? And Germans contributed to science and mathematics. They did the largest contribution a little later than French. So French, they contributed a lot in math with Poisson, Laplace, and anything which has a terminology, French terminology, it's something older than 200 and 250 years, okay? So that's an old piece of information. When it comes to linear algebra, since it carries some German terminology such as Vera-Vetiake, unique values or unique vectors or eigenvectors. That is some German contribution which happened like 100 years ago when quantum physics was developed. They noticed that a lot of variables, when they solve a differential equation, they figured out that it's best if they construct the values or the variables in these mathematical constructs that looks like a matrix. Okay, so 100 years ago, a student could not take a course called linear algebra. If you go to university, you ask Dirac, you say, okay, I want to take this course because I cannot understand your equations. He'll say, there is no such a course, there is no such a textbook. But from that point onwards, we got the development of linear algebra, which is as simple as solving, so this was linear equation. So linear algebra, it is as simple as solving this equation. 3x is equal to 6. Okay. Question is, what is x? So in this case, you could say, what is x? We can say that x is equal to 2. So this is linear algebra, and all of this linear algebra is also prepared, or it solves all of this problem. Ax is equal to b, where A is a matrix, x is a vector, and b is also a vector. And now, with this mathematical construct, you can solve any type of problem. Okay? So every problem is solvable using these. Sorry. So, after we discuss the eigenvalues and eigenvectors, this is the most important aspect, because these eigenvectors, they can help us to do the correct change of bases. So here, we're talking that we have a definition of a specific problem in a specific domain as here. Then, with the help of eigenvectors, we can choose a new domain over which we can solve the same problem in a correct way. And but this happens only for specific matrices, which we will call those square matrices. Okay? In order to generalize this change of basis, etc., we have developed a new but a new approach, which is singular value decomposition. Singular value decomposition. The singular value decomposition, it does something similar with what eigenvalues and eigenvectors did, but it does this, we call this one SVD, and this helps us to follow the same procedures or to offer a solution to the problems when the matrices are not square. So here, this is a generalization of this previous problem. So these will be, so to say, the major topics that we're going to cover during the whole semester. So then the next important information is the textbook that we're going to follow. There are many classical textbooks are used for linear algebra. For this semester, we have selected linear algebra written by two authors, which is Anthony and Harvey. Okay, you can find the title of this book even in the syllabus. The title is Linear Algebra Concepts and Methods by Martin Anthony and Michel Harvey. So this is the first textbook. The second one is a book which is written by Gilbert Strand. This is also a very classical textbook. I strongly suggest, actually you can read both. You can find the first one slightly easier, and the order of the topics is also a little different. But I strongly suggest to go over the exercises in Gilbert Strand, as they really educate you a lot, because they are developed over few editions of the book by the same author. So the book has kept improving. It's really a wonderful one. But for didactic reasons, we also choose to go over this textbook for the sake of the order of the topics presented. And in a way, it looks a little simpler. Of course, material is almost equivalent, but the first primary textbook is this one. You can find this one from the library, or you can purchase either one of these two textbooks. Now, this is the general information on the course that we are going to cover. Now, the thing is that whenever we discuss about a specific data, let's call it a data, you don't always have a point, okay? Whenever you represent something, sometimes a single data point is not enough, okay? So you might generate a vector or a series of given parameters. For example, I can ask you the following question: what would you expect for linear algebra to be? Would you expect it to be an easy course or a difficult course? You can write this one on the chat section. I can go over your comments and expect you to write something over there.
Easy.
Okay, let's switch to the comments. Maybe I'll go over your answers. Easy, difficult. Don't speak, just write over there. Writing on the chat section is also a sign of your presence. I'm going to take attendance based on whether I find your name written over there or not. Easy, medium, okay. You are refining the space over which we can categorize this course, okay. So it looks like you are counting this one as an easy class, okay, a medium class, or a difficult class, okay. And based on your answers, I see that you, Tony, of course, frankly, we will try to help. I won't be alone, okay? We got a lot of mediums. That's a good sign. So, so let's say, I see that in this class we have present around 60 students. Out of 60 students, let's assume that 20 said easy, okay?
I'm sorry, Professor, we can see that board very well.
You cannot see what?
We can see that side of table.
Okay, well,
You
everybody.
want to remove the chat team.
I can't see it.
أنا أشوفها.
Well,
وهي pin.
I'm sure some of you already see it. Is there anyone that sees that part of the board?
Yeah, we
Don't
see.
matter.
Yes.
Yeah,
I can see it.
yeah, we can see it.
Okay. If you can see it, then here we're talking about around 20 students say it's easy, and now around let's say 30 students on the y-axis. We're plotting the histogram. Okay, so and this is 30 students expecting the course to be medium difficulty, and let's say another what is left 10 students say it's difficult. Okay, so here we have an expected evaluation of the difficulty of this course, and we can also assign here easy is 1, medium is 2, difficulty is 3. Okay, that's fine. So always, sometimes when you go to a doctor, they say, how much does it hurt? You say, how can I answer this? They tell you, give me a score 1 to 10. Okay, and they say 10. Okay, so it hurts a lot. So similarly, we can assign 1 as being easy, 2 as medium, 3 as difficult. And we can even draw a distribution like this. Okay. At the same time, we can also ask the following question. What would you expect to be the grade in this course? Okay. A, which is 10, B is 9, C is 7, D is 6, and F is any grade from 0 to 5. Okay. So that's another question. And if we draw here the scale, this is going to be the F, this is the D, this is the C, we get a B here and an A. And we can assign here 1, 2, 3, 4, 5. I can ask you now the question, what is your expected grade in this class? So can you write down in the chat section, what is your expected grade in this course on a scale from 1 to 5, okay? So you might get an A, which is a 10, a B, a 9, a C, a 7, D, 6, and F, 0 to 5. I can read your comments. B, okay, we are being very realistic. I expect to see more A's. Okay, Erwin, don't be so depressive. Okay. Erwin, yes,
What do you mean, what kind of grade we expect?
Well, you're taking this course, in a few months you'll see a grade in your transcript. So what is your expectation, judging by
our capabilities?
Yes, your capabilities and what you are expecting, whatever expectation you could have, okay? Of course, any students in a university is going to aim somewhere around here, judging also based on the fact that you chose computer engineering, which is a tough department. Yes, so your expectation. I saw an F. I never expected to see an F. Okay, maybe it's just when I'm going to write it here. D, there were almost no D's. There were few C's. And there were a lot of B's. And there were also some few A's. So let's say that this is the grade expectation of yours when you take this class. Okay? Then, at the end of the semester, we don't know for sure, but let's assume that we get an expectation that is going to look like. So let's assume that in red, we write down what the final grade is going to be. Okay? These were your distributions, and probably we get a distribution that looks like this, okay, in blue. And the correct grades are going to be probably less B's than you were expecting, and maybe a few more C's, so C's around here, we get more D's and a few F's. So the distribution then is going to look like this. Okay, so the distribution in red and the distribution in blue, they are slightly different. It's hard to get a perfect match. But then, if you want to compare two students, one student, let's consider this is student 1. Student 1 had an expectation of linear algebra of being easy. So then here we have a vector 1. Student 1 also was expecting to get a B, okay, which gets a score of 4, but in the end got a grade of C, which we're writing here as 3, because in red we wrote down the final grade, okay. Then we can have another student 2 who was expecting that linear algebra is easy, and this student 2 was expecting to get an A, okay, and finally, at the end of the semester, got a 5, okay, got also A. So we can have all these different combinations, right? It's so we can have another student that thought that the linear algebra is difficult, was expecting a C, and C in this case is a 3. It's a 3, and finally he got also a 3, which means he was expecting a C, and here he got a C. So these are possible combinations between, and each one of these vectors is going to represent a student. It can also happen that another student says 1, 4, 3. Here we can have 1, 4, 4, and so on. So now, how can we compare these students? Let's think for a moment. This is the x-axis, this is the y-axis, and here we have the z-axis. So the first student thought it was easy, so we have 1, 2, 3, and then was expecting a grade of 4. 1, 2, 3, 4, 5, so it's here, and then got a 3, 1, 2, 3. So the first student is 1, 4, 3. This is 1, 2, 3, 1, 2, 3, 4. Okay. This is a 3D graph. It's slightly difficult to do a very good job to show this here, but this is going to be somewhere here, here. So we get this data point. Okay, if you draw the graph, it's going to be something coming up like this. This is the first student. The second student is 1, 5, 5. So we are here 1. 5 is here, the other 5 is here, so the next student is going to shoot somewhere here. We come 1 unit to the front, so here we get another vector, which is going to look like this. Then another student thought the class would be very difficult, would expect a 3, another 3, and here we can get a score, which is somewhere like this in red. Okay, so sorry, this is not perfectly to scale, but here you can see that some students, if you compare, for example, these two students, which are almost very close, and I mean this 1, 4, 3 and this 1, 4, 3, if you only compare these two in terms of their expectation for the course on the scale of difficulty, their grade expectation and the final grade, it looks like very close to each other. If we try to project this one in a two-dimensional space, we could also classify them something like this. So we can have a vector here, another vector here, and maybe some other students like this. So when we look at a series of data, okay, we collected only 3 inputs. We can collect even more. We can say, for example, you're expecting a grade of A in linear algebra, a grade of A in programming, a grade of A in calculus. This vector from 3-dimensional, we can go to 5. And after you do this, we can plot these vectors on this data, and we can check for the similarity between any two students. And if the vectors, which in this case is a feature vector, so let me call this one, it's a feature vector. we can compare how similar or how the same two vectors are, and we might notice that these vectors, we can even cluster them. Okay, so we can say that there is a group of students that are very close to each other in terms of their expectation, in terms of their expected grade, and in terms of their final grade. Now, so we can do clustering. Okay, and this one we can do this based on the using the matrix. So this is a feature vector. Okay, let me call this one a feature vector, and these feature vectors, they can be compared after we assign a metric. Okay. So feature vectors, we compare them using a matrix. Okay. What is a matrix? A matrix is a quantitative measure which can check how much similar they are with each other, or how much they correlate with respect to each other. And in the case of the vectors, one way to do that is, for example, to check what is the angle between any two vectors. So if the angle between any two vectors is small, we call that similar. But if the angle between two vectors is large, we say that they are not that similar. So we can have a look at this angle theta here. Okay, so this is why we may need to use this mathematical construct, which in this case we call it a vector. We can have constructs which are a little more complex than vectors, which in this case we can call them matrices. Okay, so let me erase this part. And let's see, so we have, let's assume that this is a vector A, which has values of 1, -1, and 2. This is a vector, and this is composed of 1 row and 3 columns. Okay, we're going to talk more in detail about this one. And then we can have another matrix B, which we can denote this one as 1, -1, 2, 0. Okay, so here we see a mathematical construct, which is called again a matrix, but has 2 rows and 2 columns. Okay, 2 rows because we find the first row, the second row, and in this class you could see me denoting a vector as a single-sided vector side, and a matrix probably with a double-headed arrow on top of the constant. Okay, now. These are the matrices and the vectors. Now, why do we use the vectors? We can say that in principle, vectors is a way to denote or to enter data. Now, we use computers to help us in several tasks, and even though humans have very good perception of distance, of visual perception, and at different levels, we are good at providing an instant qualitative analysis easily, humans, okay? But machines or computers, they are very good, once we write a very good algorithm on a specific problem, they can provide a very good quantitative analysis, okay? So if you look at the sky sometime during the night, and then we look back again after 2 hours, we can provide a qualitative comparison between the 2 stages, or between 2 images that we perceive in our eyes or in our retina. And then, but asking how many stars are less or more, or how much they have moved, we are not very good at it. Okay, we are good at quantitative analysis, but quantitative no. But if you provide these 2 images, photographic images, to a computer, computers can do a very good job at quantifying the similarities, or quantifying the motion of the stars with respect to Earth, or who knows, some other changes that might have happened. So for quantitative analysis, we often give this task to computers for them to do this at a faster rate and with a higher accuracy. In order to do this, we have to use concepts which are based on linear algebra. For example, if you want to give an image, if you ask a child to evaluate, let's say, two images, children or even grown-ups, they're very good to say that, okay, I'm seeing a tree, okay, that's a tree, then you show another tree, children can still say, okay, this is a tree, this is also a tree. But for a computer, once you show to a computer a tree, what they see is they see values that are going to look like this, okay? It's going to see numbers. So it's going to see an array of numbers. And here you might have a 0, here you might have a 12, and 11. So then maybe here another 11, and it goes 127, 127, 125, 125. Okay, so this is what the computer sees. So here we're going to give a matrix or an array of numbers out of which a computer has to figure out whether what is looking is a tree or something else. Now we have technologies moving forward very fast, and good car companies like Tesla, for example, they are interested into having self-driving cars, and for self-driving cars they incorporate or they use high-quality cameras to in their vehicles, and then in these vehicles they are going to acquire at a high rate data sets that look like this matrix, okay? And they have to make decisions at specific instances, what to do at a specific case, and each time they're going to see numbers like these, and they have to perceive whether it's a tree or a person, okay? So out of this array of numbers, a camera or a computer has to figure out whether they can simplify what they are seeing, whether they can extract a feature vector which corresponds to a feature vector of a tree. In principle, this tree might have this feature vector. Now, another tree is going to look like this, but probably a person looks like this. A computer, what is going to operate on, is going to continuously calculating feature vectors. And the moment that a newly calculated feature vector is close to a reference tree feature vector, it's going to say, okay, this is a tree. You have to do this or that. And then, similarly, other objects are going to have different feature vectors. So, and in order to extract these feature vectors, in order to give meaning to this matrix of numbers or to this array of numbers, all the mathematical operations that we're going to learn this semester are going to be used extensively. Well, one of the major concepts that needs to be employed or needs to be used is the concept of eigenvalue analysis or eigenvalue calculation, eigenvalue extraction, and so on. So once you do this, and these concepts of eigenvalue, eigenvector, or basis analysis, they also have equivalency with principles which can be considered as diagonalization. So diagonalization is also a very essential concept, which you're going to listen to me a lot. I'll mention this one during the end of the semester. And my job is to make clear to you that linear algebra is important, it's easy, and I have to convince you that it finds uses in very complex problems, okay? And linear algebra, I think we said before a few minutes, that is made up to solve this equation, okay? Any problem in mathematics, it can be written in this form, where A is a matrix, X is a vector, and B is also a vector. So complex operators, they can be written in the form of a matrix like this. We just need to know, to learn the tools of how to manipulate them. So this is what we need to do, or this is what we are going to see in linear algebra. We can give another example of a matrix. So we can have a matrix C, which is going to look something like 2, 0, 0, 0, 1, 0, 0, 0, minus 3. For example, here we have another matrix, which is composed of 3 rows, okay, and 3 columns. So it has 3 rows, 3 columns. We call it a 3 by 3 matrix, At the same time, we can consider this one as a triangular matrix, but we are going to go over these definitions in detail. So it's a triangular matrix because anything below the diagonal is zero. Okay. This is also a diagonal matrix because the non-zero elements, we can find them all along the diagonal. So these are the elements that we are talking about. So again, matrix, 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 but in specific case of this matrix, this makes this a vector. Now, if you like, we can have a 5 minutes break, and we can meet in after 5 minutes to continue the second part of the course. Okay? Are you okay? You'd like to have a break?
Yes.
Okay.
Yeah, that's good.